Today we start on important topics of functional analysis, bounded functions. We first write the definition of bounded functions. Okay, let X be a non-empty set, X be a non-empty set, and Y be a norm space, Y be a norm space. Okay, then Tx to Y, then Tx to Y is said to be bounded, is said to be bounded, is said to be bounded when this one is bounded if supremum of X belongs to those set norm of Tx less than plus infinity. Okay, that is there exists m greater than 0 such that norm of Tx less than equal to m for all x belongs to x. Okay, now then we call an operator T is bounded, just bounded. Okay, this operator T is bounded when we'll write this definition. Let X be a non-empty set, Y be a norm space, and X if T to X, Tx to Y, Tx to Y is said to be bounded if supremum of Tx less than infinity. Okay, next we consider pointwise boundedness and uniformly boundedness. That means boundedness family of mapping. Okay, so we erase these things now. We erase this portion. Then we write pointwise bounded. Okay, pointwise bounded. How this one happen? No, we first write same thing in definition way. Let X be a non-empty set. Let X be a non-empty set. Okay, and Y be a norm space. Y be a norm space. Okay, next, and tau subset of f x y, and then the family tau, then the family tau is said to be pointwise bounded, is said to be pointwise bounded if for each x belongs to x, if for each x belongs to x, supremum of norm of Tx, T belongs to tau less than plus infinity, where x belongs to x, and that is there exists mx greater than 0 such that norm of Tx less than equal to mx for all t belongs to tau. This family, that means family is called pointwise bounded. Okay, let X be a non-empty set and Y be a norm space, and tau some family of functional of linear operator from X to Y, then the family tau is said to be pointwise bounded if for each x belongs to x, supremum of tau x, norm of tau x, norm of Tx, where t belongs to tau less than plus infinity. Then there exists, we find mx greater than 0 such that this one holds. Okay, next we talk about uniform bounded. Okay, uniformly bounded. This one is pointwise bounded. Now we erase this portion and now going to further uniformly bounded. Uniformly bounded. Okay, now we write The definition: let X be a non-empty set. Let X be a non-empty set, and Y be norm space. Y be a norm space, and tau subset of if X Y. Then the family tau is called. Then the family tau is called. Then the family tau is called uniformly bounded. Uniformly bounded if supremum of norm of Tx t belongs to tau less than plus infinity. For each x belongs to x. Okay, then this one implies that is there exists m greater than 0 not depending on x such that norm of Tx less than m for all t belongs to tau and x belongs to x. Okay, then this family is called uniformly bounded. Then supremum of this equal to less than plus infinity and this one hold. Okay, now we're going to another definition. If xy be norm space and tau belongs to bxy, then tau is pointwise. Then same thing, supremum of tx less than infinity and tau is uniformly bounded, then supremum of tx less than infinity. But here just m depend upon x and here m does not depend on x. Okay, now we're going to one important proposition about this bounded function. Okay, this proposition tell us that let xy be norm spaces. Xy be norm spaces. Let xy be norm spaces and let tn be a sequence in bxy. A sequence in bxy such that norm of tnx is convergent. Such that tnx is convergent in y for each x belongs to x. Okay, and define tx to y by tx equal to limit n tending to infinity tnx. Okay, for all x belongs to x. Then first t be linear, second t belongs to bxy if norm of tn is founded. Now, so that tx plus y equal to limit n tending to infinity tn x plus y. Okay, this implies that limit n tending to infinity tn x plus limit n tending to infinity tn y. This implies tx plus dy. Okay. T of cx limit n tending to infinity tn cx equal to limit n tending to infinity c tn x equal to c of limit n tending to infinity tn x equal to c of tx. So t linear. Okay. Now we're going to tvxy if norm of tn is bounded. We erase our portion. Now let x belongs to x. Let x belongs to x. Then norm of tn x less than equal to norm of tn into norm of x. Okay, this implies that limit n tending to infinity tn x norm equal to norm of tx. Okay, equal to limit n tending to infinity norm of tn x equal to limit infimum of n tending to infinity norm of tn x. Limit n tending to infinity infimum of norm of tn norm of x. Hence norm of tx less than equal to k norm of x. Now k equal to limit n tending to infinity infimum of norm of tn. Hence t is bounded with okay norm of t less than equal to limit infimum of n tending to infinity norm of tn. So we prove this proposition. Okay, now we're going to further discussion of bounded uniform principle, but today we will not discuss bounded uniform principle. We start first category Baire category theorem. Okay, now we erase this portion and going to further discussion of category and definition of some. A subset M of matrix space A subset M of a matrix space is matrix space X is said to be is said to be rare or no higher tens in X if its closure if its closure M closure has no interior point has no interior point. Okay, now second, rare or no higher tens, that means one subset M of a matrix space X is no higher tens when if M closure has no interior point. And here we write measure or of the first category in X if M is the union of countably many sets, each of which rare in X, each of which rare in X. Okay, that means M, when we call about first category, we call about M is first category when M is the union of countable many sets, all are no higher tens in X. That means all closure have no interior point. This collections of union is M, then M is called first category or measure in X. Okay. Next we going to non-measure or the second category or the second or of the second category in X if M is not measure in X. Okay, M is not measure in X. So we write these three definitions of measure. Okay, now we going to, that means we going to a Baire category theorem. We write first category, second category, and also no higher tens. This one is rare, this one is measure, this one is non-measure. Okay, one subset M of a matrix space X is said to be rare when this M closure has no interior point. Measure when or first category, that means belongs to first category when M is the union of countable many sets, each of which no higher tens in X. Non-measure when of second category in X, M is not measure, that means M is not first category, that means M is not the union of countable many sets, each of which no higher tens in X. Now it's going to further this Baire category theorem. Okay, one important theorem which handles functional analysis. Write first statement of Baire category theorem. Okay, Baire's category theorem. Now if a matrix space X not equal to phi is complete, if a matrix space if a matrix space X not equal to phi is complete, it is not measure in itself. It is not non-measure in itself. Non-measure in itself. Hence, if X not equal to phi is complete and X equal to k equal to 1 to infinity ak, then at least one of 1 ak contains a non-empty open subset. Contains a non-empty open subset. Okay, where ak are closed. Okay, X equal to this, where ak closed. If a matrix space X not equal to phi is complete, it is non-measure in itself. Hence, if X not equal to phi is complete and X equal to this union of AK, where AK closed, then at least one AK contains a non-empty open subset. Okay. Now we're going to proof of this Baire category theorem. This one is so easy. Okay, that means we first a matrix space complete when it is non-measure in itself. Non-measure means it belongs to second category. Second category means that means it not is the union of countably many set, each of which no higher tens. Okay, so this implies that X equal to this and at least one AK contains a non-empty open subset. Then this one is obviously in belong to second category. Okay, now we're going to prove of this theorem. Right proof. Suppose the complete matrix space are measured in itself. Okay, suppose the complete matrix space X not equal to phi or measure in itself then X equal to measure in itself means X equal to union of mk, k equal to 1 to infinity, where each mk is no higher tens in X. Okay, where with each mk is nowhere tens in X. Okay, rare means no higher tens. Okay, then we shall construct a Cauchy sequence. We shall construct a Cauchy sequence pk whose limit is p, is in no mk. Okay, then we shall construct a Cauchy sequence pk with limit p is no mk, is in no mk. That means no mk contains this limit. Okay, then thereby we prove this one. Then some contradiction is arrived. Okay, then we going to further discussion. We reach all portions. Then now going to further discussion. By assumption, M1 is rare in X. M1 is rare or no higher tens in X. Okay, this one is better. No higher tens in X. Okay, then M1 closure does not contain a non-empty open set. Does not contain a non-empty open set. Okay, but X does. But X does. Okay, this implies M1 closure not equal to X. So simply, hence the complement of M1 closure. Hence the complement of M1 closure equal to X difference M1 closure. Okay. The complement M1 closure of M1, okay, is not empty. Is not empty and open. And open also. Okay. Next, we may thus choose a point. We may thus choose a point we may thus choose a point. Which point? A point P1 in M1 closure complement. Okay, and an open wall and an open wall about it. Say B1 equal to B1 epsilon 1 subset of M1 closure complement. Okay, where epsilon 1 less than half. By assumption, M2 is rare in X. M2 is no higher tens in X. Okay, then so that M2 closure does not contain a non-empty open subset, so that M2 closure does not contain a non-empty open subset. Okay, because this one is no higher tens, then hence it does not contain the open wall. It does not contain the open wall B P1 epsilon 1, or here if half epsilon 1 is greater. Okay, this implies that this implies that this implies that M2 closure complement intersection BP1 epsilon B P1 half epsilon 1 is non-empty, is not empty and open. Okay, so that we may choose an open wall in this set. We erase portions so that we may choose an open wall in this set, an open wall in this set B2, say B2 equal to B of P2 epsilon 2 subset of M2 closure complement intersection B P1 half epsilon 1. Okay, then we're going to further where this epsilon 2 less than half epsilon 1. Okay, by induction we thus obtain a sequence of ball. By induction we thus obtain a sequence of balls Bk equal to Ppk epsilon k, where epsilon k less than 2 to the power minus k. Okay, such that Bk intersection Mk equal to 5 and Pk plus 1 equal to Bk plus 1 subset of Bk or B subset of Bpk half epsilon k. Okay, here epsilon k less than 1 by 2 to the power k epsilon k minus 1. Okay. Then subset of Bk k equal to 1 2 dot dot dot. Since epsilon k less than 2 to the power minus k epsilon k minus 1, the sequence Pk of the centers is Cauchy. Of centers be Cauchy and converges. Say Pk converges to P, belongs to X because X is complete. Okay, now we find a sequence pk which converges to p because X is complete. Then what we found? We found for every m and n greater than m, we have bn subset of b pm half epsilon m, so that d of pmp less than equal to d of pmpn plus d of pnp. Okay, then this less than half epsilon m plus d of pnp, and this also convergent to, we erase our portions also. This also converges to half epsilon n. Okay, half epsilon m, the h n tending to infinity. Then hence p belongs to Bm for every m. Since Bm subset of mm closure complement, we now see that P does not belongs to m for every m, so that P does not belongs to union of mm equal to X. This contradicts P belongs to X. Okay, then Baire category theorem is proved. That means this contradict means X is not complete, but here obviously given X is complete, so this one, that means our assumption is wrong. Okay, so this one is that means X obviously contain one non-empty open subset. Okay, so today we stop here.